Hello everyone. This week I'm going to pick up where I left off last week with regards to using DXC to use HLSL with Vulkan. What I said last week that I would do this week was show you how to incorporate HLSL into an existing Vulkan project, because I'm assuming that everyone who is watching these videos already uses Vulkan. One of the best resources that I have found to figure out how to use the Vulkan API is Sascha Willems' Vulkan GitHub repository. It has a crazy amount of examples of basically every feature in Vulkan, all the way up to ray tracing, that you could possibly want to use. So what I'm going to do is I'm going to download this repository and go through the steps necessary in order to convert one of these samples into HLSL from the GLSL that's given. Now, what's really nice about these examples is actually that there is, in this data shaders folder, an HLSL counterpart for every single shader that's used. So you can actually already use HLSL in these samples. But I'm going to show you how we could do this with DXC and how we could translate our existing GLSL into HLSL. All right, so I'm going to go ahead and download this repository, and it has some subnodules, so I'm going to recursively clone those as well. All right, now that that's done, let's go ahead and open it up. So what we're going to want to do is we're going to want to see if we can even get this repository building. Now we could just select one of these existing kits, and I might as well. So let's just grab the AMD 64 2022 release edition and try to build it with CMake like this. Now it's going to warn us that the CMake policy is that we're using an older version of CMake, but we can see that it's going through and building all these source files. And you can see the build exited with code 0, so it just worked. Now there are a bunch of executables that are in here, and we can go ahead and try one out. So I'm going to grab a launch.json script, and this is just exactly the same as it was before. And if I press F5, then we'll be able to select one of these applications. So let's try one, maybe SSAO. And what we'll see is it fails to launch. The reason that is because there are a bunch of assets that these samples try to use that are not a part of the repository, for good reason, because these assets are really large. So what you could do is you could either, if you have Python installed, run this Python script, or you could just manually download the zip and extract it yourself. So here I have that asset pack, and within it is this data folder. This data folder is going to need to coincide with this data folder here. And we can actually see in this README that there is a link to this zip file if you want to download it. So what we can do is we can take this data folder, take these files within it, and just extract them right into the data folder here. So let's drag it in. There's a README that's going to conflict, so we'll just skip that one. So now we have all the extra assets in here, and if we press F5 now, we'll see that it actually launched. And there are a ton of examples in this repository that you can try out. What we're going to do, however, is we're just going to convert one simple example, this push constants example, which I believe has a great compromise between simplicity to understand and a good number of features that are unique to Vulkan HLSL as opposed to general HLSL. So let's go ahead and copy in those configuration files that we created from last video. So we have the CMake presets, the VC package configuration JSON, and the VC package JSON. And we can also see that here that we're specifying that we want to use Visual Studio 2022 as our generator. The reason this is a 17 is that's actually the version number for 2022. It's a little confusing because there's also Visual Studio 2017, but I assure you 17 refers to Visual Studio 2022. So the problem with using Ninja is that this repository actually tries to use OpenMP because Ninja chooses Clang, and we can't have that. So we have to use Visual Studio 2022. Now what we need to do is we actually need to link all of these programs to DXC. And the easiest way to do that would be to go into the CMake list.txt and scroll down to the bottom here where it says that there's no Win32 libraries to link yet. And what we're going to do is we're just going to add in call to find package, and then also a link libraries call, just like these other ones for the other platforms, to DXC. This link libraries call applies to every single target that is created after the call. So that includes all the targets created by the base and the example subdirectories. Now what we can do is we can go ahead and take a look at the examples subdirectory. And I said that we wanted to look at the push constants example, so let's open that up. And we can scroll down until we see that we're loading this shader, pushconstants.vert.spurv. And that's because these shader files are actually precompiled into spurv. What we want to do, however, is integrate DXC to allow us to compile the source code directly. And so what I'm going to do is I'm going to take these two lines of code, copy them, and say instead that I want to do push constants vert and frag dot HLSL. So I'll go into the data folder, shaders, GLSL, push constants, and I'll create two new files, push constants underscore frag.hlsl and push constants underscore vert.hlsl. So what we're going to want to do is actually generate the shader code from these files. So we're going to modify this load shader function to actually do what we want. Now, before I go do that, I'm actually going to add one extra argument to these functions that specifies whether or not this is a spurv binary file or its text file to be compiled. So I'm just going to say false for these ones that are commented out and true for these two new ones. All right, now we see we get an error, and that's because that's not the function signature of load shader. So let's press F12 and go to load shader and add that extra argument. So we'll say bool should compile, and we'll also add this to the declaration. And I'll specify a default argument so that anywhere in the code that this function is called already just automatically uses the old version. So we'll say false here. Now in the implementation side, we're going to forward this argument to this next function. But I also need to specify the shader stage to DXC of this shader text file for it to compile. So I'm also going to add the stage argument here. So I'll say stage and should compile, and I'll add those also to this load shader signature. So let's go over here and add in those two new arguments. So we have the VK shader stage flag bits and our Boolean to specify whether it should compile. And these as well, I will specify to default in the case of calling this function as we did before, or as Sascha did in this code before. So I'll add these and say that this is false by default, and this shader stage is default constructed by default, because we're only going to use this stage variable when we are compiling the shader code ourselves. So it doesn't actually have to be the correct shader stage. So now in this file, we have this load shader function. All of this code below is what we're going to want to do if we're doing it in the old method. So we'll say if should compile, else we'll do the below branch. And this loads the shaders in as binary and creates the Vulkan shader module from that binary data. What we're going to do, however, is use DXC to create that binary data from the text and then create the shader module. So let's go ahead and paste in my code that does this. So we load the file in, we have a string to put it into, then we skip to the end of the file, we reserve the number of bytes that the if stream is ahead of the beginning of the file, and then we skip back to the start of the file. Then we assign into the string with a pair of iterators, the beginning and end iterators of this if stream. This end iterator is empty just because the default construct iterator is the null iterator, which is what the iterator will be when it gets to the end of the iteration. We then have a shader module and module create info that we populate with the spurv buffer size and code data that we get from this HLSL to spurv function. We haven't yet created this, however. So let's scroll up to the top, and what I'm going to do is I'm going to create this function directly. What this is just, as you would expect, a function that returns a vector of uints. If you remember back to the original video, we did some pretty simple code in order to compile this HLSL into spurv binary code. So this is actually all that's necessary in order to create it. So we'll go ahead and copy all of this. And instead of printing here, I'm just going to return spurv buffer. Looks like I misspelled that. And of course, we don't have DXC included in this file yet, so let's go ahead and do that. I'll grab those headers from before. So now that we're not using a string view, we can specify this character pointer directly as well as this size. So let's see if this compiles. So this didn't compile because I went ahead and used the C++20 feature right here, but we don't need to. So let me remove it. I can also go ahead and remove the string view header because we're not using that anymore either. Now what we need to do is we need to have some valid shaders. So I'm going to quickly, miraculously paste in some shader code that should compile. So I'll paste a vertex shader in and a fragment shader in. And let's just try and run it. What we'll see is that we get a failure. If I go to retry this, we can see it happens as an assert on the return value of VK create shader module. VK create shader module fails here because the code that we provided was actually vertex and pixel shader code. But to the compiler, what we specified was that it was a compute shader. So it didn't generate any of the relevant shader code that we wanted it to. What we can do, however, is instead of hard coding it to the compute shader, is use that shader stage parameter that we set up before. So let's add some code in to check what stage we're compiling, whether it's the vertex, fragment, or compute shader. We'll specify the correct command line argument. If now I press F5, we can see that it's successfully compiled. But we're ignoring a pretty fatal flaw to this method of using HLSL, which is that if I were to put in a compile error in one of these shaders, we would just get an error that is due to the resulting spurvy buffer just being empty. So we didn't get any error information from this. What we want to do is to ask DXC whether or not our compilation failed, and also get from DXC on a compile error what the error message was. And we can do that in a pretty similar way to how we extract this shader object file. So let me just paste that right in. What we have is a com pointer to a UTF DXC blob interface, and we get the DXC out errors message from the result output. And then we check whether or not this error message is valid and that the string length of it is greater than 0. And then we default construct a string. We resize that string to the size of the buffer from this error message, and then we fill that string with that buffer data. Then what we can do is we can just call messagebox, which is a Windows utility function, to display this compile error. And the reason I'm not couting this to the console is because this is actually a Win32 application which doesn't have a console attached to it. Now, if I press F5, what we'll see is we get a DXC compile error saying that it expected a semicolon where we had this error on line 8. It does, however, say that the file name is HLSL.HLSL, which we of course know is not the truth. In order to get the real file name, what we would need to do is specify to the args just the exact file name. So we would say pushback L, whatever we want. So maybe we say this is our fragment shader. And if I press F5 now, what we'll see is that it comes from the fragment shader. So I'll leave it as an exercise to you all to pass the HLSL file name through to this function so that it can correctly specify it in the arguments, and also convert it yourselves to a wide string, just like the arguments require. And finally, what we'll do is we'll go through and convert these existing GLSL shaders into HLSL. So let me delete all of this shader code here, and we'll start with the vertex shader. So obviously what we want to do is we want to create a main function. Now this isn't going to be a void function because in HLSL, how we transfer from the vertex shader to the fragment shader is through the return value of this function, as opposed to having these in and out variables specified in global scope. So I'll specify a couple structs, one that is the vertex shader input, and one that's the fragment shader input. Now this vertex shader input is the struct that we're going to use as the input to this function. So I'll call this input, and the fragment shader input is what comes as an output to our vertex shader. So we'll say that that's the return value. Now the vertex input are these attributes here. So we'll specify them as we would in HLSL. We want a float 3 that is the position, we want a float 3 that is the normal, and we want a float 3 that represents the color. However, you can see that in Vulkan, we have to specify a location. So we can go ahead and do that in our HLSL using a Vulkan extension to HLSL which is built into DXC, where we specify vk : location. And in here, we can say it's at location 0, 1, and 2 for each of these. And then what we need to do is we also need to create the input for the fragment shader, which is the float3 color, as you can see here. It's a vec3. So another thing that we need to do, we need to take this definition of a uniform buffer object and be able to use it as well. So we need a float4x4 for all of these. And instead of making this a uniform, what I'll do is I will say that this is a struct called UBO, and that there is a constant buffer that represents it. So we'll say cbuffer UBO, and it's at register B0. That's corresponding to this binding of 0, B being buffer 0. And we just say that it's UBO, UBO. Now we have access to UBO within our main function. Another thing that we need is this push constant. So to do that is we just declare another struct, which I'll call push constant, or just push. I'll call push, and it has a float4 color and a float4 position. And now to use this push constant, as opposed to saying layout push constant, what we do is we say, using another Vulkan extension, vk : push _ constant, and then declare PC as type push. PC is just a name. We could call this push constant or push const or whatever we want. I'll just call it PC. And now what we need to do is we need to populate our fragment input using the vertex input. So we'll declare a struct fragment input, I'll call it result, and I'll say result.color is equal to the input.color times the push constant.color.rgb. And that's exactly what we see over here. But now we need to do some other things. We need to somehow specify this GL position variable. Well, there is no global variable like this in HLSL. In order to specify the position of the vertices as we do in GLSL using GL_position, what we need to do is we need to specify in our vertex shader return struct that we have a float4. We can call it whatever we like, but we have to annotate it using SV_position. And what this says to the compiler is that this is our quote-unquote GL position variable. So then what we do is we'll say we have a float3 local position, and it's the XYZ components of the multiplication between the UBO model matrix and the float4 input.position, 1.0. So this should return the actual vertex position transformed by the model matrix. And then what we'll also do is we'll calculate the world position by adding on to the local position the push constant.position variable. And now we can say that result.position is equal to the multiplication between the UBO.projection matrix and the multiplication of the UBO.view matrix with the world position. And then all we have to do is return the result. Now, what we'll go ahead and do is convert our fragment shader, which is a lot simpler. And that's because all it does is take in those inputs and use them as an output. So we just have our float4 main, because what we want to return from main is a pixel with color float4. But we need to specify that this float4 represents the target color attachment. And this takes in our fragment input. So I'll say frag input, and I'll just say that I want to return input.color. And one thing you'll notice is that this out color also had a location. And we could specify, just like we did before, this VK location, but we could also use a more HLSL standard, which is specifying a attribute name. We could call this main color, for example. And all we have to do is also call this variable down here, main color. But there's a bit of a standard to how people usually name these. So I would recommend saying that this is color 0, and that obviously has to match with the one down here. Now input color is a float3, so we'll want to extend it to a float4. And so now, hopefully, if I press F5, we'll see that the program runs with no error. And that's not the truth. The reason that I recommend using these annotations is actually because they're required to be given to these variables no matter what, even if they're not going to be used. So the vertex input also has to have these names given to them. So I'll just give them what the standard name would be usually, which is position, normal, 0, and color 0. So now if I press F5, we can see that we've got it running. As I said at the start of the video, there are these HLSL shaders for all of the examples that are available. So you can go ahead and take a look at the fragment and vertex shaders that he has written for these specific examples if you want to try and convert one of the other programs for yourself. Last thing I wanted to note is about these compiler arguments. These are just a select few of the arguments that you could add, but on top of these, you could, for example, also have an optimization flag, for example, O3, and this will tell DXC to optimize the resulting SPIR-V. All right, I think that about covers how to convert your GLSL into HLSL. So thank you for watching.